University, MTech from IIT Kanpur, and PhD from IIT Bombay in Aerospace Engineering. Our coach session for co-chairperson is Dr. Sanjay Singh, Head of Institutions of Amity Institute of Aerospace Engineering, Amity, Uttar Pradesh. So, with this thought, I would like to request Dr. Sanjay Singh sir to felicitate Dr. Om Prakash for this one. All right, sir. Yes.
So we'll begin the session with the first paper presenter of paper ID number 4, numerical analysis of four-body wake effects on the parachute performance for re-entry space application. Rudresh M. from Dayanand Sagar College of Engineering will be presenting this paper.
So myself Raghav Mehrotra, and I'll be sharing the screen now. Is my screen visible?
Yes, it's visible.
Yeah. So I'll be starting the presentation now. So good afternoon to all the panel members present. So myself Raghav Mehrotra from Dayanand Sagar College of Engineering, Bangalore. So I'll be presenting the paper presentation regarding numerical analysis of four-body wake effects on parachute performance for re-entry space application.
Can you just switch on your video if you have question?
Yes, sir.
Before that, I would like to tell you the rules and regulations of the presentation. So the presentation total consists of 15 minutes. That is, first 10 minutes are for your presentation, and the next 5 minutes would be for, and the last 20 minutes will be for your question and answer Q&A. And your first bell will be rung at the 8th minute to warn you about your presentation. And finally, at the 10th minute, 2 bells will be rung to tell you that your presentation.
Okay. Okay. Yeah. So just a second. Coming to the first slide, defining the outline of the presentation. I'll be covering first goes with the introduction, what my paper is about. So as we all know, when for the re-entry, that space capsule are there, as we all know that Apollo mission is there, for that some space capsule was there. So while landing, it has to land softly because all the passengers, astronauts will be there inside it. So it is one parachute is used, either a parachute or a cluster of two parachutes can be used for creating the drag, that is the wake effect, in order to slow down and increase the drag such that the astronauts will land safely on Earth. So for that, first goes with the introduction. An aerodynamic drag system is a component that interacts with the movement of air fluids, particularly when the material it's made of can deform significantly. So basically, what we are telling in the introduction is that whatever the presence of the front part of a body has a significant impact on the aerodynamics properties of a parachute. It causes the area of disturbed air known as the wake effect remains in the parachute canopy. To simulate the interaction between fluid and structures in spherical parachutes, so what we'll be doing is, in this paper, what we have done is we have validated the wind tunnel test done by DRDO on parachute and four-body and parachutes. So coming to the next slide, what is the methodology? What we have done in this paper? So first we started by modeling the geometry, whatever was there in the paper for one particular four-body. We have scaled down it. Like in the paper only, it was mentioned that the scaling factor is used as 6.43:1. So with respect to that, we have created the model. I'll be showing that in the next slide. So apart from that, once the model was ready, then we shifted to ANSYS for the numerical simulation, starting with the grid independency test, and then going further, we started the we have done the analysis for the same, like a four body alone four body, and also the four body with the parachute. And that analysis was done at different speeds, because we don't know that at what velocity the space capsule will be reaching us. So we have calculated the drag values at different velocities, suppose 20 to 50 meter per second, and also at different side slips, because we don't know at in the environment how the profile or whatever component is falling, at what side slips it will fall. So in the DRDO paper, like in the wind tunnel test, what they have done is they have done it at different side slip angles. Suppose 0 to 15 degrees side slip angle they have taken at of order 5, like 0, 5, 10 and 15, and calculated the side force as well. So the same thing goes with our paper as well. And also like this is just for the four body I told. Coming to the with the parachute, as we all know that when the parachute is elongated, there is one string that is called the, that length is called the riser length, and all the tangential lines which are there, that is called suspension length. So based on different types of riser length and suspension length together forming as wake distance, we have also calculated at different wake distances what is the drag and what is the significant effect of it on the same. Yeah, so comes the modeling of the geometry. This was pretty straightforward, that we have scaled down the model, and you can see the dimensions here. 0.485 meter was the maximum diameter of the four body, which is mentioned here, that we have taken from the model which DRDO has already done in the wind tunnel test. So to validate that, we first started with the grid independency test. So why we need a grid independency test basically? So if we are doing the analysis in the starting, then we need to have some particular amount of mesh size, like, so that we can say that yes, this mesh is proper and suitable for us for defining our problem, like whatever solution we want. So what we did, by changing the course, find all the mesh settings and also the element size, we carried on with different types of mesh. So it kept on increasing the number of elements, and as you can see in the graph, after 27,110 elements, it is becoming straight line, which means the mesh is going to be converged after 27,110 elements. So what we did, we just took that mesh settings, like the mesh settings which were there, at which we got the CD values as constant. The initial value, which you can see here as my cursor is pointing, that is our mesh setting. So next comes the boundary conditions. So boundary conditions, we just assumed it to be exactly like the one which is there in the wind tunnel. This is the assumed condition, because we don't know actually what is the condition with respect to the wind tunnel which CRDO has tested. So what we did, we have just giving the boundary conditions. One on the inlet side, we kept on changing the velocities with respect to our this thing, with respect to our needs, that 20 meter per second to 50 meter per second, but the relative pressure was zero because it is a closed chamber, so we kept it as zero as the relative pressure in the boundary conditions we have given. So next comes the results and discussion. So once the analysis was completed, then in ANSYS CFX, in ANSYS fluid flow CFX, this analysis was done and we got the drag values. So calculating the coefficient of drag, why I am saying this, because in the paper which we have referred, they calculated the CD values, like the coefficient of drag values. So calculating the area from the geometry, density we all know that it is at sea level. So calculating it for different velocities, we have calculated the coefficient of drag at different side slips. So which you can see in this slide. And next slide will tell that what is the difference or percentage error in the same. Yeah. So now you can see that this is the four body which we have just analyzed, only the four body at different side slips angle. You can see 0, -5, 5, -10, 10, -15, 15. You, everyone might be thinking that what is the difference with -5 and +5? So here it will tell that it will not be the same, that the flow around the body will not be the same if it is at -5 or +5. It differs, like all the components are like whatever fluid is flowing in the air, so it will not be the same for -5 and 5. So that is why at all the side slips it was done and at different velocities, and the mean value was taken. And here CD wind tunnel mean values which you are seeing is basically the one which we have taken from the DRDO paper. which was published. So you can see here the percentage error is under the engineering limit, which is around 9 to 10%. So next slide comes with the cluster of one like single parachute. So what we have done here is you can see this that four body is there the same, and we have prepared a parachute as well, which I showed earlier in the dimensions, that whatever dimensions were there for a particular parachute, and this riser length kept on changing. So this analysis which we have done, like we have done all the analysis, but for the presentation point of view we are showing only one. So this was for 10D. 10D, what is 10D? 10D means weight distance, 10D. D is the diameter of the parachute. So with respect to that, we have done this analysis, and we can get to know that only 1.49% of error was there with respect to CF numerical data and the experimental data, which is the wind tunnel data. So here you can see all the data are like tabulated, and 5D, 7.5D, 10D with the different side slip angle and different velocities it is mentioned, and also the wind tunnel mean values are mentioned. So percentage error is there, and you can see here the percentage error is pretty less compared to the only four body wake effect. And next comes the limitations and future scope. So what is the limitation in our presentation and the work which we have done is that we have just done it with respect to single parachute, not the cluster of two. So in the future scope, we will be completing that as for the cluster of two parachutes, because it's like cluster of two parachutes is necessary, because if suppose if one parachute is there, it will be creating drag, we all know. But if two parachutes are there, it will be creating more drag, and it will make our life easy for the astronaut to land. But the main catch here is if two parachutes are there, they might entangle between them, and it might come down as a free falling body. So that is one limitation. Sorry. Then comes the conclusion. As I earlier told, four body wake effect on the performance of parachute, which functions as a retarder and helps in decreasing the descent rate of the space capsule smooth landing. A design analysis was performed to predict the drag and coefficient of drag at various side slip and velocities, and also at different riser length. Simulation was carried out in ANSYS finite element program for different set of inclusive materials, different riser length, and different side slip angles, out of which wake formation is only one for one set of data, whereas other sets are tabulated, which I have already showed. Now, the main conclusion which we have got from this work is coefficient of drag values were calculated, obtained from CFD, in general agreed with the wind tunnel data and with a very small error percentage. Thank you.
Presentation.
Sorry?
Few questions, and I'm particularly interested if you're planning to do the PFD or winter this, considering the relative motion of the body, means the riser length and the suspension lines. In between these two lines, if there is an angle.
So, your voice is not clear. Can you please repeat?
If you are going to model the suspension line and riser line and the angle between these two.
So, I'm just able to understand riser length and suspension length. Apart from that, can you please repeat? I'm so sorry.
So, if you are considering both in straight line, so I'm just thinking if you are which are going to give some angle between these two lines. This could be motion.
So, sir, like as I showed earlier, this like I'll clear once again that whatever suspension lines are there, if you can see my cursor, this is the suspension length and this is the riser length. So, based on that, we have done that at different riser length and suspension length, but together it will be forming as 5D, 7D, and 10D, which you can see on this slide, riser and suspension line. And length for riser length is, yeah.
That is, I was just asking you the angle if you are looking for angle between these. Right now they are straight line.
Hmm.
I look forward to
Yes, sir. So angle, regarding angle, you can see here it is mentioned 20-degree conical ribbon parachute. So that 20-degree conical ribbon which we are mentioning is defining the angle, and at different angles, you mean the full parachute wise forebody. So for that we have done the analysis, like you can see here. Yeah. So this beta, that is a side slip angle. So suppose if this my hand is the full parachute and the forebody, suppose this is going down, which is zero side slip. Then when it will be 5 degrees, then how it will be performing?
Your side slip angle basically will go to that angle.
Yes, sir. Yes, sir. So 0 degrees, 5 degrees, 10 and 15 at different we have done, and you can see here in this table only below this 10D with the side slip angle as 10 degrees and different 1.49% error which is there, which we have showed. So in this figure you can see that is at 10-degree wake distance, which is the length from the parachute till the forebody, and it is at a 10 degrees angle that we can't make out here, but it is at a 10.
Your relative angle as well as the relative length also.
Yes, sir. Full body is at 10 degrees because it will be like what, because of the moment that parachute is there, it will try to rotate the body in that angle as well, which is there. Like suppose 10 degrees side slip is there, so the full body will also move.
Next presentation. Thank you for your information.
Yes, sir. Thank you, sir.
Thank you so much, Raghav. Now I would like to invite paper ID 45, which is a multi-layer microstrip antenna for broadband monopulse tracking technique. And the presenter is Brijesh Panchal from Amity Institute of Defense Technology.
Rajesh, are you there?
Yes. Just 1 minute. I'm sharing my screen.
All right. Go ahead. Yes, you can start your presentation. Rajesh, can you turn on your camera, please?
Yes, 1 minute. Is my screen visible?
Yes, it is visible. You can proceed.
Uh, okay, so my name is Rajesh Panchal. Uh, I am the student of Amity Institute of Defense Technology. Uh, so my research work is on multi-layer microstrip antenna for broadband monopulse tracking technique. These all are the topics which I will cover in the presentation. Uh, let's first see the abstract. The current work process a single element of microstrip patch and air antenna that is performing well as a prominent radiation patch element and can be developed for monopulse tracking systems like seeker application due to its broad bandwidth, effective directional pattern, low profile conformal design, low cost, and ease of manufacturing. A single unit of multi-layer aperture coupled microstrip antenna has been developed for X-band frequency range with a bandwidth of 1 gigahertz. The single element of multi-layer antenna structure is designed to obtain a low return loss, wider bandwidth, better directivity, and better gain. For a multi-layer microstrip antenna that operates at a center frequency of 10.9 gigahertz, the return loss of minus 42 dB with 6.3 dBi gain, having VSWR less than 1.5, has been achieved by analyzing using the software called CST Microwave Studio EM Simulator. This is the introduction. So, monopulse tracking is a method of radar tracking that can track a target reliable in both azimuth and elevation. So, multiple antennas are employed in monopulse tracking to capture the echoes or signal reflected from the target at the same time. Uh, to extract useful information about the target's position and velocity, the monopulse tracking approach compares received signal from the different antennas. Uh, the the system can correctly estimate the angle of angle of arrival of the target by analyzing the phase and amplitude variations between the signals. The main idea underlying monopulse tracking is to generate two or more parallel beams that are significantly offset uh, from one another. These beams are created by mixing the signals from multiple antennas that have distinct relationships. Uh, these beams are created by mixing signals uh, and these signals are then merged in a specific circuit called monopulse comparator to produce an error signal that can be used to track the target. Uh, Here I have designed multi-layer microchip patch antenna. So multi-layer microchip patch antennas have been preferred in many situations where single layer microchip patch antenna may not match the needed criteria due to their better performance. Sorry, sir, I cannot hear you clearly. Hello.
Hello. Rajesh, can you hear?
Yes, sir.
Yes. So you please change the slide. Okay, you are now right now at the slide number 4, introduction.
Uh,
So next
sorry, sir,
slide,
your voice is very low.
you have to finish your presentation within 10 minutes, right?
Yes, sir. I will finish in 10 minutes, sir. So the use of multi-layer structure allows for more effective energy coupling from the feed system.
Please show your findings. It is okay. Introduction is okay. Please change the slide. I'll show you results.
Okay. So this is the antenna design I have made. So this antenna is working in the X-band frequency range and operates on 10.9 gigahertz. So this is the front view, rear view with slot of the multi-layer antenna. So there are 6 layers. First layer on the top layer, it is a rectangular patch, which is a main radiating patch. The another layer is patch substrate of material Rogers 4003C. Then third layer is bond ply material which has material Rogers 4450B. The fourth layer is ground, which is of copper material with a rectangular slot. Uh, that rectangular slot is used for the aperture coupling between the feed line and the rectangular patch. The another layer is feed substrate of material Rogers 4350B, and the last layer is feed line. These are the dimensions of all the layers, uh, dimensions and materials. These are my result. So This is the S parameter result, which is showing a return loss of minus 42 dB at 10.9 gigahertz. This is the gain plot. We can see that in X band it is continuously increasing, and at 10.9 gigahertz the gain is 6.3 dBi. This is the 2D and 3D radiation pattern. If we see the 2D radiation pattern, we can clearly see that the directivity of the antenna is 6.57 dBi. In E plane beam width, it is 76.2 degrees, and in H plane, the beam width of the antenna is 100.8 degrees. So for future work, I have made one single antenna element. We can, after that, using this single element, we can make an array of multiple antenna elements along with the monopulse comparator. Monopulse comparator can be made by branch line couplers to work as a monopulse tracking technique for radar system and missile systems. This is my conclusion. So this research work process a multi-layer patch antenna with aperture coupling approach that works on the 10.9 gigahertz, having broad bandwidth of 1 gigahertz. It is claimed that by analyzing its characteristic and optimizing the design parameters, it may be employed in monopulse tracking systems for X-band missile seekers application due to its highly directive nature. To obtain different parameters as per the specific application, it can be more optimized through variations in slot which is made on the ground plane. The major performance parameters such as antenna gain, bandwidth, and return loss have been observed. So these are my references. Thank you. Sorry, sir, your voice is very low. Sorry, sir, I cannot hear you. Hello?
Yes, sir. Yes, sir. Yes, please. Answer me.
Hello?
Vijesh, is the question clear to you?
No, sir.
Okay. Can you hear me?
Now, yes, I am here. I can hear you.
Accordingly?
Yes.
Okay. My question is, we have used multi-layer microchip antenna. You have performed this section, right? So what are the advantages of your over the conventional antenna?
Sir, for monopulse tracking techniques and especially for missile seekers, I am focusing on missile seeker application. So, for missile seekers, mainly the patch antennas are used because of their it can be easily manufactured. Because for if we see a missile seeker antenna, it is a very means the array of antennas are many and the antenna patches are manufactured in a circular or any squared manner. So for easy of of implementation. Uh,
Okay, thank you. Thank you very much, Rajesh, for your presentation. Thank you.
okay, thank you so much.
Thank you, Rajesh. Now I would like to invite paper ID 53, the design and implementation of FTT using Verilog HTL for radio altimeter signal processing. The presenter name is Sarvana Kullari Sairama from Amity Institute of Defense Technology.
Thank you. Good afternoon, everyone. I think you can see my screen and you can hear me clearly, please. So, what I have done, the study and the implementation I have done is the implementation of SFT using
There
HTL
is
for
no disturbance from your end. There is disturbance from your background.
uh, sir, we're talking about the noise. Hello.
Yes, you are audible, but there's a lot of background disturbance from your end. Can you
Yes,
please
sir.
check?
Sorry that actually I couldn't know that noise. I'm sitting in a place which is not maximum.
Uh, you can connect your microphone from your mobile, or you can either switch from to your laptop if it's possible.
I tried it, like
Okay, it's now.
sorry sir, can I continue? Like I think we'll
Can
continue
you
like
turn on your video, please?
yes, sir, turning. Yes, sir. I
Savannah,
think
can
you
you
can.
turn on your video, please?
Yes, I can turn on the video, which is I'm gonna have why is it so much blurry? Sorry, because of the background light, it is so much blurry. Shall I continue? Hello.
For the next
Savannah,
Sarvana, can you hear me? Hello.
With that, we would like to call our next participant.
The paper ID is 89, Studies of Curing Time and Curing Temperature of AP. Studies of Curing Time and Curing Temperature of AP.
Uh, yes,
Sorry.
hello.
The presenter is Fawad B. Fondekar from Birla Institute of
Yes, sir. So that's the participant, जो presenter है.
from Birla Institute of Technology, Mesra.
Yes, hello. My name is Prabhat Fondekar. Am I audible to everyone?
Your voice is not audible. Abhat, your voice is not
Hello.
audible. Turn on your camera, please.
Yes. Am I audible to everyone?
Yes, you are visible. Can you share your
Okay,
screen?
okay, okay. So shall I start? Okay, I'll share the screen first. Yes, I hope it's clearly visible to everyone.
Yes, it is visible.
Okay, okay, fine. I'll start now. Okay, so my name is Prabhat Dattakumar Fondekar. Currently, I am working as a research scholar in the Birla Institute of Technology in the specialization of rocket propulsion. Okay, My study name is Studies of Curing Time and Curing Temperature of the AP-HTPB. AP means the ammonium perchlorate and HTPB is the most commonly used fuel binder, that is the hydroxyl terminated polybutadiene. So best composite solid propellant. Now the contents. So first initially we'll talk about some introduction of our work. Then after that the formulations, the density measurement, the methodology basically, then the conclusion and the references. So introduction. So solid propellant is one of the most reliable and most commonly used stage as a booster stage I'm talking about, right? So for to make means the manufacturing part of the solid propellant is play a very important role. So mainly there are three steps of manufacturing the solid propellant. First one, the formulation and the preparation of propellant slurry. Okay. Second one, the casting and the vibration process, and the last one is the curing process. So each of these three steps are very important. So formulations means you have to take all the ingredients. The ingredients means basically the oxidizer, fuel binder. If you're making the composite solid propellant, there are so many ingredients are involved in it, whether it is a curing agent, cross-linking agent, plasticizers, additives, etc. The next one is the casting, casting according to their mold and mandrel, and the last one is the curing process. Okay, so basically we have to keep inside the oven for a specific period of time. So my study is focuses on the curing, not a curing part, focusing on the formulation part. Okay, so for this study, I have taken HTPB as a fuel binder. HTPB means hydroxyl terminated polybutadiene. That is the most commonly used fuel binder till now. So now the thing is, the HT for curing the HTPB, it takes around 6 days. Okay, it takes around 6 days, and the temperature is 60 degrees Celsius. So 6 days is a very high time period. So I'm trying to reduce that time period and focuses on the each and everything regarding to it. Okay, so for the formulation of solid propellant, I have taken these ingredients. First one, the oxidizer means the ammonium perchlorate. I have taken the O by ratio 4, means 80 percentage of the oxidizer part and 20 percentage of the fuel part. So from the 20 percentage, 13.48 is the fuel binder, that is the HTPB. Binder is used to bind the oxidizer particle. Second one, the plasticizer. Plasticizer is focuses on the enhancing the mechanical properties of the composite solid propellant. That is the DOA, means dioctyl adipate. Next one is the curing agent. Curing agent enhances the curing properties of the propellant. So basically it reduces the curing time. And most commonly used the TDI or IPDI, means toluene diisocyanate. These are the curing agents we can use. And the last one is the bonding agent. It is used to like combine or provide the good bonding between all the ingredients. And the glycerol is most commonly used. Okay, so these are the ingredients list that I have used for my study. Now, as I have told you, the traditional curing time is a 6 days, and the traditional means the conventional curing temperature is a 60 degrees Celsius. Okay, so 60 degrees Celsius and the 6 days, these are the traditional cases. So for my study, I have increased the curing time and simultaneously I have decreased the curing time. Okay, I have increased the curing temperature and decreased the curing time. So I have taken the 5 examples, including the 5 examples means the cases, including the conventional case. Sample number was first with the curing time 6 and the curing time 60. The sample number second with the 5 days of curing with the 70 degrees Celsius. Next one, the 4 days of curing with the 80 degrees Celsius. Sample 4 is the 3 days of curing with the 90 degrees Celsius, and the last one is the sample 5, the 2 days of curing with the 100 degrees Celsius. Okay, so these are the some casting, the picture of casting of the propellant slurry, and the next one is the prepared propellant sample. Now the first, now coming to the methodology, the first test I have done, that is a density measurement, because the density should be high in the case of solid propellant. So in this case, I have used two methods. First one, for the experimental density, I have used the most commonly used volume displacement technique, the mass of the propellant divided by volume of the propellant. And the second one, for the theoretical density, I have used this formula, for calculating the theoretical density. Okay, so these are the results. You can clearly see in the graph the sample 1, sample 2, sample 3, sample 4, and the sample 5. As we increases the temperature, the density of the propellant is getting decreased. So basically, it's indicating that the propellant samples will become a more brittle. Okay, propellant samples will become a more brittle at the higher curing temperature. So it will negatively affect on the packing density. Now coming to the second methodology, that is the burn rate. I have used the Crawford bomb setup, means the strand burner setup for carried out this burn rate testings at the different pressure conditions. First one, the atmospheric pressure condition. Second one, the 200 psi. Third one is the 400 psi. The nitrogen gas, that is the inert gas, I have used for testing all this propellant samples. And I have used this formula. The burn rate is equal to distance between the fuse wires and divided by the burn time. Fuse wires means it is the distance of a propellant strand itself. Next one, these are some results I have got from the study. The pressure, the first one is indicating the pressure in the PSI, the sample 1, sample 2, and so on. As you can clearly see, as we increases the pressure, coming to the sample 1, increases the pressure, the burn rate is also increases, that is a standard condition. But for the sample 2, sample 3, sample 4, and the sample 5, that is increasing the curing temperature, right? So increasing the curing temperature, the burn rate is also going to be increased. So basically, it is because of the sample is getting more porous. Okay, so sample is getting more porous. So some air gaps are present in between the samples. So because of that air gap, the burn rate is getting increased. Now coming to the second result, next result, the mechanical property testing. So I have used the UTM, means the Universal Testing Machine, for carried out this tensile testing. And these are the dog bone shaped samples I have used for my testing. Okay, the first picture is the standard conventional sample, means the specimen. Second one, the during testing, you can clearly see the breaking point, and the last one is the after testing picture. Okay. Now, from the mechanical properties, means the mechanical testings have formulated these results. As we increases the burning temperature, the Young's modulus is also getting increases, and at the same time, the elongation at the break point is getting decreases. So it is clearly indicating that the propellant sample is getting more brittle and more hard, right? And the last one is the hardness. Hardness is also carried out. This testing is also carried out by using the hardness tester, the Shore hardness tester. The hardness is also getting very high. Okay, so it is clearly indicating that the propellant sample is getting more hard and more brittle because the elongation at the break is going to be decreased. Now these are some standard conditions. So basically, I have formulated this result from the testing, and these are the standard conditions. Means your propellant mechanical property should be between this range. These are the standard range of the composite propellant sample. Basically, I have referred this standard range from the book of H.S. Mukunda. Young's modulus should be in between the 30 to 40 megapascal. Second one, the elongation at the break 6 to 25%, and the last one is the hardness 60 to 80 Shore hardness. Now we can check it from this list. Only sample 1 and sample 2 is lies in between this range. Only sample 1 and sample 2 is lies in between this range. Otherwise, the sample 3, sample 4, and sample 5 goes beyond that length. So we can't use these samples for our findings. Now coming to the FTIR testing. FTIR means the Fourier transfer infrared spectrography. These testings are carried out for checking the functional groups are present in the propellant sample. What kind of functional group? If you increases the temperature, then how it will affect the functional group, whether it will changes or not, etc., etc. And the next one, the inert gas, and these are the input parameters I have taken for this testing. Now coming to the results, the graph. The first one, the sample 1, this is a sample 2, sample 3, and the sample 4. You can clearly see all the graphs are nearly same. The peaks are little increasing, decreasing as per the strain, but all the peaks you can clear these are the functional groups. Okay, these are the functional groups are present inside the propellant sample. But coming to the sample number sample number five, sorry, it is a sample number five. The additional functional group is involved in it. Okay, it is clearly see the you can clearly see the additional functional group. This is a functional group of isocyanide. So it indicates that when we increase the curing temperature, the more amount of isocyanate is indicating in the propellant grain in the range of 2000 to 2300 uh, centimeter per centimeter. This is a wave number basically. Now, what is the significance of it? So when this HTPB and the TDI, HTPB is the fuel binder and the TDI is the curing agent. When these two things are reacts with each other, then polyurethane will form. So this is a conventional process. But when we increases the temperature, it will again react with the isocyanate and it will form the aliphenate linkage. So
What can,
this is indicate. Sorry.
what can you hear us?
Yes.
So please complete your presentation within 2 minutes.
Okay,
Yeah.
okay, okay, sir. So this is indicating the aliphanesh linkage. Now coming to our last study, the thermal decomposition study, it is carried out to check the all the exothermic and the endothermic reactions. So these are some graphs, the DSC and the TG curves. These are the thermal decomposition studies. Now I'll show you in the tabular format the sample one, sample two, and sample three, and the sample four. These are the samples. In this case, we can see the only three graphs. Okay, only not a graph, only three peaks. So first endothermic, exothermic, and third one is exothermic, and all the peaks are lies in between this same range. Okay, but the last sample we can see the additional peak, and this additional peak is indicating the aliphenate linkage. Okay. Now coming to the results. So the first peak, the second peak, and the third peak that we have already seen, and the last peak it is because of the aliphenate linkage that we have seen in the sample number five. Now coming to the conclusion from this, we have found the bond rate testing means the bond rate is going to be increases, but at the same time it is become a more brittle, so that's why the packing density is getting decreases. Now next one, the mechanical properties, only sample one and sample two is lies in between the range, otherwise all the rest of the samples are lies beyond the range. And the FTI studies says that because the in the case of sample number five, we can see the aliphenate linkage, and the same about the last study. So from this, all the studies, we can conclude that only sample 1 and sample 2 means with the curing temperature 60 degrees Celsius and the 70 degrees Celsius, we can use it for our future things. So that is my conclusion. And the references, these are the references I have used for my study. Thank you so much. Thanks so much.
If you analyze the impact of different this during the time of opposing solid propellant and humidity.
Sorry, sir, the effect, sorry, your voice is not.
I didn't say, did you analyze the effect of different atmospheric conditions and humidity on
Okay,
your result?
did you analyze the effect of, can you please repeat it?
Atmospheric condition. I'm sure if atmospheric conditions are different. Okay, so this will affect the cooling time and the this your cooling temperature. So a different atmospheric condition. What is the effect of?
Okay, the atmospheric conditions you are talking about, I think. Am I right, sir?
Right. Did you
So
get me?
basically, uh,
My question is clear to you?
no, sir. Actually, your voice is cracking.
So
Sorry for it.
university was for this cooling time and cooling temperature of APST based composite solid propellant, right?
Yes, this is sir. Your curing time and the curing temperature. Yes.
What is the impact on this cooling time and cooling temperature of different atmospheric conditions?
Okay, sir. See, basically, this curing time and curing temperature is very, very important because in the productivity manner. So currently we are using the 6 days method. The HTPB based solid propellant is it required the 6 days of curing time. That is a very huge time period, as we can say. But when we able to decrease it, then the productivity of the propellant sample is getting increased. But so that's why I have tested all the samples. As we increases the curing temperature, obviously the curing time is getting decreases because it will getting more hard and brittle. So from this study, I have concluded that the sample 1 and sample 2 is only lies in between the limit. Otherwise, the sample 3, sample 4, and the sample 5 is lying beyond the limit. So we can't use it for our future scope and for our industrial manner. So we can use the sample 1 and sample 2 only. Even for the temperature, yes, we can use the 60-degree and the 70-degree. Otherwise, we can see the problems in the case of the physical properties, the chemical properties, and or other mechanical aspects of.
Thank you, Gulab, for this good presentation. Thank you so much.
Okay, thank you so much, sir. Thank you. Nice.
Uh, so now I would like to request Sarvana Sairama from Amity Institute of Defense Technology to present their paper on design and implementation of FFT using very low HDL or radio or signal processing. Their paper ID is 52.
Thank you. Sorry for the technical issue earlier. I'm just setting my screen. I think you can hear me now clearly and clean. Lot more clear and clean than before. So basically, I'm presenting a paper based on the study and implementation I have done on the FFT using very low system for radio altimeter signal processing. So this is the outline. These are the content I'm going to cover in this presentation. Abstract, introduction, literature review, the FFT what I have done, algorithm I have used it design implementing this very low implementation and the conclusion. So coming to the abstract, basically what I did is like I implemented a Verilog RTL for fast Fourier transform for field programmable data type, which is FPGA, which is basically being used in digital signal processing method for radio altimeter. So what I actually want to do is like I'm using a radio altimeter, which I need it to work for the um, radar and Doppler resolution algorithm. And the algorithm is basically being done in digital signal processing, which digital signal processing is basically using a FPGA for as its processor, and where this fast Fourier transform is being applied as an algorithm for in that particular FPGA. So here, what I have implemented is I have implemented a basic 8-bit in FFT radix2 method using decimation in time with a butterfly diagram. So coming to the introduction, why I need FFT for radio altimeter. As I said, FFT is needed for radio altimeter because I need to implement a range and Doppler algorithm. And FFT is one of the best methods for using the uh, range and Doppler algorithm. Not only that algorithm, for other algorithms also. And why only FFT? Why not DFT? Why not any other signal processing methods? Actually, basically we'll focus on DFTs, which DFTs in DFT also we have so many things like linear filtering. Not only linear filtering, we have convolution, correlation, spectrum analysis, and why we need to choose 50 when we have this many options in DFT. So what happens in DFT? DFT is actually basically is for the original sequence of frequency, which means if we have 10 bits, and when we are going to sample when we are going to bring up a analysis like analyze it, it is going to make it into double length square. So what happens here? It is making the signal more complex while analyzing it, while sampling it. So it will be having issues with memory, RAM, and everything. So when it comes to FFT, what FFT is basically it will assist DFT, and what it will do is basically uh, the algorithm that will approach a signal. It will kind of make a signal into frequency points. It will make it into sampling points, and it will basically convert it into and different points where it frequency sampling points, so it can be analyzed easily, and it converts a digital signal into analog way to, so it can easily be sampled, it can easily be viewed, and its application is not basically used in radar only. If, sir, sir.
Results quickly.
Yes, sir. I'm directly following up. I'm trying to complete the presentation as soon as possible. So when it comes to applications, applications are not only used for radar. So it is started with audio, video, not only audio videos like IR, LiDAR, everything. So I mean, the literature review I have focused on implementing the RTL very low for 50. And coming so coming to the main methodology I have used, like this is basically normally FFT is based on will be basically working on two different things. Where I have mentioned it not clearly, I should mention it DIT and DIF, which is estimation in time and estimation in frequency. Sorry for the mistake. Where uh, what estimation time will do, why it will be more useful for the effective, why it will be more flexible with my algorithm is because what it will do is it will separate uh, even and uh, odd terms and even and odd samples into separate different ways, and it, with the help of a field factor where you can see here W power k, which is basically a field factor. What it will do, it will basically divide two, like basically divide our n by two samples into two different domains, like two different ways, so it can be making it into easy complex way. So it will be using the odd plus fiddle factor into like even and odd. It will separate both of them, so it can be easily sample. It can easily analyze it for the next process. So when it so moving forward, like based on this thing where I have implemented an algorithm, I have used the same formulas for my own uh, process. I have used a pathway, used a flow chart for implementing a Verilog algorithm. So these are the results of my implementation. So where I'm taking a 8-bit real and 8-bit imaginary data for my uh, FFT for my, as an input. So here you can see the small x re dot small x re dot 7 is the real input, and here is the imaginary input I'm giving, and in the same place I'm getting the FFT output sampling where we can if we manage to if we manage to make these things, we manage to take it move it forward towards the um,
It's like to understand.
sir.
Like to understand.
Sorry, I cannot hear you properly because like it glitch with the mic.
For 3 minutes. You have 3 minutes.
Yeah, yes, yes, sorry, sorry. So here is schematic diagram I have like schematic diagram after the algorithm I have built. So when it comes to what I have did is I have proposed a destination time radix to method algorithm for FFT, which is basically requires less computation, slower calculations, because the algorithm that I have used is varying not varying the n component samples into n by 2. It will also like divide it into the with the help of fiddle factor. It will also divide even and odd differently. So it can be made it easily, and I have used Vivado software for my for this RTL implementation, Verilog implementation, and I have did the butterfly operation and everything also. And thank you, sir. That's all from my side.
Is the software, the other software is open source?
Yes, sir. We got a software is open source. We have like a standard and ML version also. So we basically use a standard version, and only few FPGAs, few processors are needed For few IPs, they need license version. Maximum regard is like basic open source. Everyone can use it. Anyone can learn.
Is there any future work you're looking for in this area?
Sir,
Future work, what do you do future work in
traveling. It's not clear. Sir. Can you just repeat it again?
future work in this area?
Specializations. Yes, I cannot hear you properly. Your voice is still breaking.
Thank you so much, Savila.
Yeah.
Savila, you can turn off your camera.
Yeah.
Can you unpresent your screen, please? Yeah. So with this, we come to an end of our technical session 3, and the best paper award will be announced at the end of in the closing ceremony of the conference. And with this thought, I would like to ask Dr. Sanjay Singh to please felicitate Dr. Om Prakash